Hello everyone, this is Amir from Audio Science Review. Today we're back to reviewing products, but also as with previous reviews, it'll be a sort of a tutorial on how to read the graphs and the underlying architecture in these devices. About a couple years ago, a company from China called Khadas or Khadas, however you pronounce it, Khadas, brought out a revolutionary product. It was a board that sort of looked like this, and for $99, it had incredible performance. That became quite famous as a result of our review, and many people bought these and used them in their own devices. So you could take them and build your own streamer, get a Raspberry Pi, plug it in, and you have yourself a very high performance product. Fast forward 2 years later, a lot of companies have come up with finished products, finished DACs for $99 that have incredible performance. So the company has come up with a second generation Tone2 product, and they've also built one with a case because case was a major issue with the first one. People try to make their own, and with just aggravation. So they now have two versions of this, one in the bare board format, which I just showed you, and also one in this sort of unusual looking case. Feels very nice in person. When I saw pictures of it, I thought it looked kind of hokey. It has an interesting innovation in that these RCA connectors look like standard RCA connectors, except that they actually have a third ring inside of them. So you can actually use a special cable which they sell, which converts, which gives you balanced output, differential output. So out of the same space that an RCA connector would take, you now can use a regular RCA, so it's backwards compatible, or use this special cable. Excuse me for reaching down on the floor. And that's what it looks like. I don't know if you can see in the camera, you probably can't. But anyway, inside this RCA looking thing, there's also the another ring here. And when you plug this into here, on the other side, now you have a 3-pin standard balance connection. So as you can imagine, this is way too big to have on a device this small. You can get mini XLRs and other things, but then if you had mini XLRs in here, then you need to have another one for RCA, and essentially you couldn't build something this compact. So pretty cool device, rubberized back, I suppose made to be a portable form factor. Kind of hard for me to imagine what the scenario is for this, in that all the cables will tug on it. And so you really need to have portability in mind and smallness in mind to care about this. Different from the original one is that we also have balanced and unbalanced headphone jacks, which I'll also cover in the review. And this is a rotary control, and unfortunately brings us to the worst aspect of this device, in that it has a bunch of options that you can select, from filter to the gain setting for the headphone. But to activate them, you have to grab this button and either push it once forward or twice forward. And then there's a ring of lights that come on. Maybe I can plug it in and, well, maybe I won't do it, mess up the video. Anyway, a ring of lights come on underneath, and how the colors are identifies, what mode you're in. You sort of turn this and the different light stands, and there's a video on it, and without it, though, you'll be totally lost. I tried, I couldn't make it do anything. Even with a video tutorial, it is atrocious. It's extremely hard to navigate through. So I struggled through it and produced the results that I wanted, but if you're going to set it once and be done, maybe it's all right. But I think this is a miss, despite the great effort that they put in it. So with that out of the way, why don't we look at the product itself as far as the review and the measurements. This details of the board, if you care to look inside and see what it's using. Classic XMOS USB interface and what have you. This is the USB-C port on the right, And there's an I2S in the form of USB-C, which I haven't seen. And but you can also use it just to have a cleaner power if you need it. I don't think you need that, and as you'll see from my testing. We usually have our standard dashboard, and I started with a balanced output. Very nice to see 4 volts output out of the DAC, and SINAD, which is a ratio of noise plus distortion compared to our signal. Our signal is this in the middle, and you can see that it's extremely good, 118. State of the art is about 121 these days, is it, or 120? And you can see where it finishes in balance mode. It's almost, it's I think number 14 or 15 from the top, but it's only like a couple dBs that separates these guys from each other. I was a little surprised that when I tested out just the RCA output without the special adapter, performance dropped more than I expected. It went down to 113 and 111. You can see the reason for it is this cluster of noise out here in higher frequencies. Looks to be some kind of noise on the ground plane of USB or something that's bleeding through. And but shows you the reason to use balanced output. It really rids you from a lot of dependency on how clean the upstream ground is in your audio product and audio system that you're building. So if you can, get the balanced output for this. You can see the effect of the RCA out as far as how much lower the dynamic ranges. We're down to 113 and 115 versus almost 120 when we use balanced output on the right. So, is it audible? Probably not, but might as well get the performance that you paid for it, although you have to buy that adapter cable, and I don't know how much it costs. So for the rest of these tests, I stay with balance. Whenever I have a balanced product, I assume you bought it because you want to use balance. Otherwise, they're usually cheaper options. One test we run is this intermodulation test, which is a 60 hertz and a 7 kilohertz, 2 tones, not 1 tone. The previous test was 1 tone. This one has 2 tones, the 4:1 ratio in amplitude. The low frequency one is 4 times louder than the high frequency one. And then we look for intermodulation patterns between these two. If the system's perfect, you put 2 tones in, you get 2 tones out. But if the system has any nonlinearities, you put 2 tones in and you get a lot more tones out. And there's also noise. This declining portion of the graph always tells you that basically noise is dominating, because as the signal gets stronger, the fixed level of noise becomes a smaller and smaller portion of the overall signal, and therefore performance improves. So here we see that when we start at minus 60 dB, we coincidentally also have minus 60 dB of signal noise ratio, or noise and distortion ratio. But as we go higher and higher, performance improves. Now, typically DACs start to then tilt back up. At this point, when they flatten, noise and distortions have become equal. And then distortion starts to get louder and louder, and it dominates when the graph tilts up. Here, we almost don't see that. So it's all basically noise. The distortion is essentially negligible in this product and beats my standard reference, which is this Topping DX3 Pro. So extremely good performance. State-of-the-art DACs are a little bit less noisy, and that's how they get that extra 2 dB of performance. Another test I run is called linearity. I feed it a 200 hertz digital signal, and then what comes out of a DAC, we heavily filter. So all we're looking at is really just that 200 hertz. And we look to see if that level is what we predict. So if I feed a digital minus 120 dB, I expect to see an analog signal that's 120 dB lower than the reference, which in this case is 4 volts. This used to be a tough test. Many DACs would flunk this. And ever since I started running it, more and more companies are paying attention to this. And now we're seeing just exceptional performance even in budget products. So here you see that even at minus 120 dB, which is this point down here, there's basically no error, 0 dB error. So this is a big number. This is 20 bits down. We've taken a 4 volt value divided by 2 to the power of 20. and still managed to get 0 deviation. So this device is probably more accurate to even below this level. So quite a nice accomplishment. People complain and say that, well, your tests are one tone. Well, so far I've showed you 2 tones, so it's not all one tone. But we also run tests called a multi-tone. There's actually 32 tones mixed together in a special way with a special phase, which I won't get into why. But a perfect system would produce these 32 tones with nothing else. We don't have a perfect system. We have some noise, and we have intermodulation distortion. Same problem I talked about before. Here, this performance is just exceptional. We see that at low frequencies, our distortion's down to -130. And at higher frequencies, usually distortion and noise increases, and we have a little bit of that maybe. But really, it's about 22 bits of distortion-free range. System that does 20 bits is already fantastic, and to get 22 bits is just amazing. Other state-of-the-art products also do that. But again, we're talking about a package, system that's a couple $100 with a headphone amp and everything built in. So job well done. Clearly engineers were paying attention. Test we run is called a jitter test. It's really not a jitter test in that anything that's spurious and unwanted shows up in this test. So we run a signal called J test, which for now I assume it just means a 12 kilohertz tone. And then we expect to just see that and nothing else. Here we see the symmetrical view of all these pulses. And when they're symmetrical, most of the time it means it's actually jitter. Because if you take a signal and you modulate left and right, you get 2 sidebands, one below it, one above it, and still was symmetrical. If they're not symmetrical, like this one here, that means that's just some source of noise inside the device. There's 2 clock modes in this thing, but heaven help me if I could figure out how to get into the clock mode to change it. It's supposed to have a clock mode that gets rid of jitter, but it was just so deep inside this set of menus there are to navigate that I did not get a chance to muck with it. Maybe the other mode makes it better. I don't even know which one is the default right now. But fortunately, these are at -130 dB, so definitely not an audible problem. The DAC silicon that these companies use, in this case an ESS DAC, they always have a set of filters. The principle of sampling theorem says that if you want to have a transparent channel, when you encode something, you have to band limit it to half the sampling rate at encoding time, at analog to digital conversion. And then when you convert the digital samples back to analog, you again have to apply the exact same filter. That filter ideally has 100% response up to the half the sample rate and then 0 after that. We can't build such filters in real life, but we can approximate them. And there are different algorithms. People have come up with different ideas of how you do this filtering. Some filters, for example, have ringing when you get close to the top. Some are slower. Some of them have time domain issues. Some of them don't. Audibility of them is quite suspect, know that. So don't go crazy over it. But one thing we do want to have is that after the attenuation happens, we want it to be essentially no signal. So we want very deep attenuation, 100 dB or better. For some reason, this DAC only attenuates down to 60 dB. I don't understand. I changed the modes, and some of them you can see they attenuate a lot, and then they go back to not attenuating. I don't know if it's a hardware problem, software problem, or maybe testing by me, but this is a standard test I run every DAC. I don't know. I haven't seen this before. So I'll be curious to know why it's doing this, because I know the DAC itself is not noisy, but why the out of band area is got very high level of noise, relatively speaking, 50 dB. So, that's hopefully a company will respond and let us know what's going on there. When you have this, I can always predict what the performance is going to be terrible in the next test. This is a frequency sweep where we digitally create different tones at different frequencies, and we sweep from 20 hertz to 20,000 hertz, the audible band. Now, what we're looking for is harmonic distortion. What is a harmonic? Is multiples of the signal that we're interested in. So a system that's perfect, if I feed it 1 kilohertz, I get back 1 kilohertz. But if it's not perfect, it may generate even harmonics, so it may be 1 kilohertz, 2 kilohertz, 4 kilohertz, or maybe odd 1, 3, 5, or maybe a mix of both. To capture the harmonics of 20 kilohertz, the second harmonic of 20 kilohertz at 40 kilohertz, third harmonics at 60 kilohertz. So we need to, when I'm running my analyzer, I need to open this input bandwidth. Even though the sample rate here is only 48 kilohertz, I have to capture more than that to be able to catch the harmonic distortions of these frequencies. Now, I could make it infinite, but then it picks up a whole bunch of other things we're not interested in. So as a compromise, I set the bandwidth to 90 kilohertz. Once it's set at 90 kilohertz, then I can even catch the fourth harmonic of 20 kilohertz. And after that, harmonic distortion usually drops off. So what this test does, though, then, it not only gathers the distortion, but the measurement is actually noise and distortion, THD plus N. N stands for noise. When the DAC doesn't filter out the outer band, as we call it, the ultrasonic frequencies, that stuff all shows up in this measurement as if they're distortion. But in reality, they're images of the signal reflected back, and they get summed in this test. And in this case, because the attenuation was very poor, you can see this graph in here in red. The original Khadas Tone board, look at how clean that was compared to this. That does not mean that this device has a lot more distortion. It just means that its filtering is not great. And in this measurement, it just looks awful. We can prove that by changing the sample rate to 192 kilohertz. When we do that, 90 kilohertz is actually in band. We don't need this filter, basically. The filter is not needed for that measurement. And you can see what happens to its performance. Now it becomes incredibly good, easily beating its last generation board. The brown and green is the 192 kilohertz version. So we've proven that this is not any kind of inherent distortion, because if we just change the sample rate, performance improves tremendously. Fortunately, this is not an audible thing, because harmonic distortion and stuff above 20 kilohertz are not audible anyway. But from engineering point of view, we measure things, we look for excellence, and in this one area, it's just something's wrong with this filter. And again, hopefully it's a firmware programming issue with the core silicon. That same chip is used in many other products that don't do this. We know the DAC itself is extremely quiet, so we'll have to see what they respond. So that's the DAC portion of it. That's using the line outs on this thing. By the way, the third connector on this is PDIF coax. There's no optical, but you have a coax input also. So switching to headphone, the original product didn't have a headphone output. It had the option for one, but they never brought it out. There's two gain settings in there here, low gain and high gain, and it ships with low gain as the default. And the low gain mode has incredibly low noise and distortion, but very little power. And I almost chucked it because I said, wow, it's got no power. Then I realized that it has a high gain setting, and I went ahead and did one more test. Because it has both balance and unbalance, I had to run the test multiple times. So if you look in here, this red curve at the bottom here is the maximum power we can get versus distortion and noise. And it's only 5 milliwatts. 5 milliwatts is what you get out of a phone dongle. So it's not a lot of power in low gain mode. But if you have a very sensitive IEM, that may be all you need. And if it is, you're getting incredibly low noise and distortion, better than my reference desktop product that's in dashed blue. If you use unbalanced, it's this gray line, and it doesn't even put out 1 milliwatt, and it gets distorted from 0.1 milliwatts. So not a lot of distortion, but so I really don't see unbalanced being usable with a high impedance headphones. Sorry, I forgot to mention this is a 300 ohm load. So, but if you go to balance mode and high gain, you get this blue graph, and now you get 52 milliwatt. For a desktop product, my standard is 100 milliwatt. If you get 100 milliwatt, you can drive almost 99% of the headphones that are out there. 52 milliwatts is still pretty good. Again, a typical dongle for your phone is 5, so it's a lot more powerful than what you would get out of a phone. The first test that we just ran, excuse me, is a test of how much voltage we have because the impedance is high. There are headphones with impedance very low, and when the impedance is very low, we don't care as much about voltage, we care about current. That's what delivers power. So running the same test now, we see that the low gain mode in red balance is still quite good. Unbalanced is still, it puts out a little bit more power, 10 milliwatts, but it's just pathetic. You need more than that. Going to balance mode in blue had this distortion hump, which was kind of unusual. Some kind of distortion sets in and then it disappears. I don't know what that is, and usually don't see a hump like that, but there's some kind of distortion mechanism that kicks in. Luckily, even at this level, still minus 85 dB, so I don't think you'll hear this one. But eventually it hits a brick wall, it runs out of current, and it clips, and it goes to this hockey stick of just shooting way up. So you obviously don't want to, get past that. Whenever a device like this has a headphone amplifier, I always listen, because listening will tell me whether this limit is actually something I can hit or not. And I use 2 test headphones always, same 2. First one is a Mass Drop Ether CX by Dan Clark Audio. And the reason I use this it has an impedance of only 25 ohms. So it's a low impedance and relatively inefficient. It brings many headphone amplifiers to their knees. And here in balanced mode, using this box, it managed to get pretty loud. I mean, it was comfortably loud for desktop use, so definitely very usable. But I could crank it up beyond that point, and it would get very distorted, very audibly distorted, and I wasn't going deaf, let me put it that way. It was very loud, but so know that there is a limit, and indeed this clipping point you will hit. We have 200 milliwatts in here. High-powered desktop amps will go 1, 2, 3 watts or even more. So we're about 10x lower than what we get in a powerful desktop amp. But remember that this is a USB powered, so it's all the juice you can pull out of the USB socket, and doesn't have an external power supply, which the high-powered desktop amps have. But you can definitely, if you have a headphone like this, you can take it on the road with you with this little device and still be all set. I then switched to HD650 Sennheiser that I use as a high impedance headphone. I have balanced cables for it, but I always use it in unbalanced mode. And I plugged it in here. It produced music, background level volume. It lacked impact, lacked dynamic range, and it certainly didn't get very loud. Didn't get distorted either. But you definitely need a balanced cable for it, at least if you're me. If you listen to very low levels of sound, then maybe you don't. And in that case, I don't even know if you need this. Just use your phone or something. So where are we on this thing? It's a little difficult to rate this product, because if that filter was perfect, I tell you, I would give it one of the highest awards I could. It would be state of the art. And usually I don't care about that filter, but it's just that attenuation is not there. And then secondarily, the user interface. I usually don't rate the user interface in my reviews. My verdict is based on performance design. I'll let you be the judge of the functionality on your own. But in this case, I just thought it was so bad that I had to incorporate it. So because of those 2 reasons, I still recommend it. I still think this is a nice option to look at, especially for size, form factor, balance, unbalanced, headphone out, and everything included in this little device. So you should consider it, but I can't give it my highest rating that I would. If they fix that filter issue, then I will highly recommend it, and I might even go back and change my rating to it. But for now, good product. I appreciate them sending it to me. I couldn't find pricing on this board. By the way, this is $200 from them. I couldn't find pricing on this. I don't know. The original one was $99. I assume this is. Maybe this is just an OEM product, or maybe I just couldn't find it. But if you use this just as a DAC, maybe you don't have to deal with all the grief of the user interface. And if it's half the price, again, you can build incredible streamers with this. I mean, you combine this with a Raspberry Pi or something, and you know, you're in heaven. Or you can stick it in the little Intel PC or whatever, however you build your streamer, and have this in there, and it'll have better performance than multi-$1,000 boutique products. Okay, thanks for stopping by, and hopefully, even if you weren't interested in this product, you learned something about the measurements and how to read and interpret them. Okay, see you in a future video. Bye-bye.